Namaskara. We will go for few more problems on DC circuits. Before I go for the other problems, I will just brief as to what we did in the last class. We considered the problems involving series and parallel. On the other hand, if you come across circuits, something like this, the problem cannot be easily solved by the network reduction technique, in the sense these two resistances cannot be combined as are considered to be in series and combined as R1 plus R2, because in between we have one more resistor R3. We cannot consider these two to be in parallel because R1 is not directly against R3, but R1 in series with this voltage source V1 is in parallel with this R3. So in that case, the network reduction technique fails here. Therefore, we have to think of some other method, and that can be by what's called as the branch current method or the loop or mesh current. One is branch current method, the other one is loop. Loop is also called as mesh. Branch current method or loop or mesh analysis. So in that respect, you can consider, in case of branch current methods, you consider I1 here, say I2 here and I3 here. Current in each branch is considered. Then go for the Kirchhoff's voltage law for this loop as well as this loop. As far as this loop is concerned, now you will observe here. Now if you start from here, for example, if I call it as say A, B, C, D, say E, F. For the loop A, B, C, D, A, as I start from here, I am going from minus to positive, that can be taken as plus V1. Then as we move this way, we are moving in the direction of the current. In that respect, the drop across this can be taken to be plus to minus, means minus, that will be equal to I1 into R1. Then when it comes to this one, it will be minus I3 into R3 equal to 0. When it comes to this point, there is no drop here, therefore it will be 0. In that respect, when you go for this other loop, that's nothing but C, E, F, D, C. As I move this way, I am going in the direction of the current. Plus to minus means minus I2 into R2. Plus to minus is minus V2. As I go this way, I am going against the current, therefore it is plus I3 into R3 is equal to 0. You will observe there are three unknowns and only two equations. It is not possible to solve. In that respect, you have one more equation, that is nothing but I1 can be written as equal to, considering the Kirchhoff's current law, it will be equal to I2 plus I3. By solving these three equations, it is possible to get the values of I1, I2, I3, from which you can find out the voltages or even the power consumed by individual circuit. On the other hand, you can go for the loop method, in which case this is R1, R2, R3, V1, and this is V2. We can assume the current to be flowing in this loop, call it as say I1, and this one as I2. There is no rule that I1 and I2 must be in the same direction. It need not be clockwise, or it can be even anti-clockwise also. However, generally clockwise is considered as it gives much convenient to write the equations. In that respect, as we go for this loop, again I will call it as A, B, C, D, E, F. For this loop, it is A, B, C, D, A. As I go from here, it is minus to plus means it is plus V1. This way it is minus I1 into R1. When it comes to this resistance, there are two currents flowing through this one. One is I1 and the other one is I2. And that can be shown to be something like this. This being R2, this is I1 and this is I2. This can be analyzed to be equivalent to this. We have I1 here, this being R1, sorry, this being R2, plus this will be I2, this is R2. This being C, this is D, same CD, CD. As I am moving here, I encounter two currents, one I1 and I2. As far as the drop due to I1, it is we are coming from plus to minus, therefore it can be taken as minus I1 into R3. It is R3. And there is one more current in this one, that's nothing but I2. As far as I2 is concerned, since we are moving this way, the current is flowing from plus to minus, but we are moving from minus to plus, therefore it can be taken as plus I2 into R3 must be equal to 0. So with that, it can be simplified as equal to minus I1 into R1 plus R3, that's it, R1 plus R3 plus I2 into R3 equal to, this will be minus V1. You can call it as equation 1. And when it comes to this loop, the loop CEFDC, as I go this way, it is minus I2 into R2, plus to minus, it is minus V2. As I go this way, it is minus I2 into R3. As far as I1 is concerned, I am going against that one, therefore it is plus I1 into R3 equal to 0 as I have come back to starting point. With that, it can be written as equal to minus plus I1 R3 minus I2 into R2 plus R3 equal to, it is V2. By solving these two equations, we can get I1 and I2. Therefore, the number of equations involved in case of mesh equation is less compared to the mesh equation or loop analysis method is less than that of the branch current method. This is much popular than this one. As we go further, we will understand how to solve these equations also. The equations can be solved by substitution method or elimination method, or it can be determinant method also. So calculators can also be used to solve the problem, solve the simultaneous equation. When you go to some problem, I will explain how to use the calculator. Coming to this problem, the power dissipated in 10 ohm resistor is 160 watt in the network shown. Find the supply voltage Vs and the total power supplied by the source. The given circuit is this. This is Vs. These are 15 ohm, 30 ohm, 5 ohm, 6, 10, 4. It is required to find the supply voltage Vs. Vs can be written as equal to, if you start from that, it will be equal to, if I is the total current, I into R equivalent must give that. So in that respect, I must know what is current I and I must know what is R equivalent also. As such, we know the resistances R equivalent can be easily found out. Later we will come to that. Now, how to find out? As we go for this, first we should know what is I. To find out I, look at this. What has been, there is some data, in that respect it has been mentioned as 10 ohm resistor is consuming 160 watts. That means this is consuming 160 watts. So with that, is it possible to find out this will be R10, the voltage across this one, V10 divided by R10 must give the power will be equal to this, or it may equal to V10 into I10, or it may be equal to I10 square into R10. So in that respect, we can go for this expression to find out what's the voltage. So therefore, V0 will be equal to power, that's nothing but 160 into 10 divided by under root. So that comes to 40 volts. Once I know the voltage here, I can find out what's the current also. What will be the current? The current through this I10 will be equal to V divided by the resistance. This is nothing but 40 divided by 10 comes to 4 amperes. Once I know this voltage, I can find out even the voltage across this, the current also here now. Obviously, I4 will be equal to 40 divided by 4, that comes to 10 amperes. And finally, this I6, this is I6, this is I10, and this is nothing but I4. This will be equal to 40 divided by 6 comes to 6.67 amperes or so. Add up everything, you will get the total value. That will be 4 plus 6.67 plus 10 comes to 20.67 is the total current. That means the current that is flowing here is nothing but that. Whatever the current that's flowing here is also flowing here, is also flowing here. I know the current. Now I have to find out what is R equivalent. R equivalent will be equal to, this can be simplified as equal to this one, these two are in parallel, that comes to 15 into 30 divided by 45 plus one resistance, that is 5 ohm, that's nothing but this one. When it comes to this one, say that it can be, the total value can be obtained in different possible ways. We can find out what's the total resistance of these two and then these two. On the other hand, we can go for this also, 1 over 1 by R1 plus 1 by R2 plus 1 by R3. In the sense, this will be 1 by 6, this will be 1 by 10, and this will be 4. That gives you the total resistance. If you simplify this, this is Vs. Say this resistance comes to this comes to 1.94. As you can observe here now, the total, the equivalent resistance must be lesser than the lowest value, that's nothing but 4 ohm. So you are getting, or it is coming to 1.94 ohm. So with that, the total resistance, when you add up this comes to 10 ohm, 10 plus 5 plus 1.94 comes to 16.94 ohm is the R equivalent. Therefore, Vs will be equal to the current, that's nothing but 20.64 into 16.94 would give the value of the applied voltage. This will be approximately 350 volt. Once I know this, what else to be? Find the supply voltage and the total power supplied by the source. The total power supplied by the source will be equal to P. This can be taken as Vs into I, or it can be taken as equal to Vs square by R equivalent, or it can also be taken as I square into R equivalent. All of them should give the same value. In that respect, if I go for this will be 350 into 20.67 will give you that value. That I have not calculated, but anyhow, this will be the value. Consider another example. In the circuit shown, calculate the power dissipated in each resistor and the reading of a voltmeter connected across 5 ohm resistor. The circuit given this is 5 ohm, this is 10 and 20 ohm, the voltage applied is 100 volts. It is a straightforward question. Calculate the power dissipated in each resistor. In that respect, I will call this one as say R1, call it as say R2 and this say R3. Power dissipated in each resistor means P1 can be taken as equal to, this will be the current square into R it will be V square by R it is V into I. But when it comes to the corresponding values, it is not just the value simply I, but what is that? In that respect, you will observe here 5 amp, this in 5 ohm, the total current supplied by the source is flowing through that. That's nothing but I square, that's the total current. When it comes to R, it is not R, but it is R1. When it comes to voltage, if V is taken as the supply voltage, then what will be the voltage across this? As such, this 100 volts is not appearing across 5 ohm resistor or across this, it is across the combination of the two. In that respect, if I call this one as say V1 and this one as say V2, this must be taken as V1 square and then this is V1 into I1. To find out the power, obviously I have to know the current as I know this resistance. How to find out the current? We know these two are in parallel and it is in series with this. Therefore, this circuit can be written as equal to, this is 5 ohm, this will be 10 into 20 divided by 10 plus 20 comes to 6.67 across 100 volts. Further, this will be equal to 11.67 ohm because they are in series. This is 100 volts. It is this. So this is I. This is also I. Therefore, I is equal to, this is 100 divided by 11.67 will give a current of 8.57 amperes. That means the current flowing is 8.57 ampere. Here also the same thing. Therefore, what is P1 is equal to, this is 8.57 square into 5 ohm will give you a value of 367.2 watts. Once I find out this one, next I have to find out what is P2. P2 can be taken as equal to, this is V2 into I2, if I2 is the current here and I3 is the current here, or it may be equal to V2 square by R2, or it can be taken as I2 square into R2. We can find out V2 and we do not know V2 yet, but we do not know what's the current that's flowing through this. However, we know here R2, if I can find out I2, it becomes easy to find out P2. In that respect, how to find out I2? Now, the current divider rule comes into picture. I know total current, I know the resistances in parallel. Therefore, I2 will be equal to the total current 8.57 into resistance of the opposite branch, that's nothing but this 20 divided by the sum of the two resistances, that's equal to this. This I2 will be equal to 5.71 ampere. Once I get this, P2 will be equal to 5.71 square into this will give you that. So, this works out to 326 watts. When it comes to P3, this will be equal to I3 square into R3. In that respect, what is I3? It's nothing but I minus I2, or you can find out the value by those similar to this expression also in that respect. I3 will be equal to, this is 8.57 minus 5.71, that comes to 2.86 ampere. Therefore, P3 will be equal to 2.86 square into 20 will give around 163.6 watts. We have found out the power in each resistor. The next one is, what's the voltage across this 5 ohm resistor? That's nothing but V1. If I connect an voltmeter across this 5 ohm resistor, it records the drop in this, with the assumption that the voltmeter is offering infinite resistance or it is not drawing any current. In that respect, V1 will be equal to I into R1, that is 8.57 into 5 will give you around 42.9 volt. So, that is the answer. In this regard, instead of finding out I2 and say I3 to find out P2 and P3, knowing V1 and knowing V2, can we find out the power also? Yes. In that respect, P2 will be equal to V2 square by R2. We know this V2 is nothing but V1 plus V2 must be equal to this. Therefore, V2 will be equal to 100 minus 42.9, that comes to 57.1 volt. .1 So, therefore, this will be equal to 57.1 square divided by this 10 comes to 326. You will observe the same answer has been obtained here. When it comes to P3, this will be equal to again V2 square by R3. This will be 57.1 divided by square divided by 20. This comes to 163 watts. If it is simplified, it works out to 163 watts. However, you will observe it has come as 163.6 watts. It's because of the rounding of values of I1, I2 or V1, V2 and other things. So, with that there may be a difference, but there is no much difference between the two values. Therefore, the power can be calculated either from the voltage consideration or from the current consideration. Go for another problem. A 20 volt battery with an internal resistance of 5 ohm is connected to a resistor of X ohms. If an additional 6 ohm is connected across a battery, find the value of X so that the external power supplied by the battery remains the same. A 20 volt battery, that is this one, this is 20 volt, having an internal resistance of, that is this is 5 ohm, is connected to a resistor of X ohm, this is X. If an additional 6 ohm is connected across the battery, when it comes to across the battery, which are the terminals of the battery? As such, the terminals of the battery, accessible terminals of the battery is only A and B. This internal resistance is, you can say, it cannot be separated from this voltage source. It is an inseparable quantity. However, for analysis purpose, it has been taken to be in series with the voltage source. In that case, when you are connecting the external resistance, it is always between A and B only. unless otherwise if it is a ideal source. If it is an ideal source, you can this point can be coming here, or you can assume the resistance to be 0. This is the first one, and the second one is this 6 ohm. If an additional 6 ohm is connected across the battery, that means if an additional 6 ohm is connected across the battery, find the value of X so that the external power supplied by the battery remains the same. What is this external power? As far as the power loss in this 5 ohm is the internal loss, while the power lost here in X is the external loss. So here the power loss will be in both X and 6 ohm. The external power in both the cases is same. Then how to find out that? In that respect, if I call this one as say I1, external power will be equal to P external 1 will be equal to, it is I square into X will give that. The value of I will be equal to I1 square. What is the value of I1? We know 20 volts is in series with 5 ohm and X ohm. Therefore, this can be written as equal to 20 divided by 5 plus X square into X. That is the one. Coming to this one, the same, this one can be written as, the same circuit can be written like this also. This is 20 volts, 5 ohm. As said, these two are in parallel, therefore it can be written as 6x over 6 plus x. If this is called as I2, which is same as this I2, then P external 2 will be equal to I2 square into the external resistance. That is nothing but 6x over 6 plus x equal to, what will be this I2? It will be 20 divided by 5 plus 6x over 6 plus x whole square into, this is 6x over 6 plus x. For the power to be same in both the cases, equate these two, wherein which you will observe the only unknown is x. When this is simplified, it results into a quadratic expression. Instead of simplifying, I will just go for a simplified version. So this is nothing but the circuit that has been, whatever that has been written on the board, you can see on the screen. Finally, it works out to, when these two are simplified, it works out to 6x square minus 25x minus 150 is equal to 0. This can be solved by usual method, or you can use a calculator also. X will work out to 7.5 ohm, or it will be minus 33.33 ohm. As the resistance cannot be a negative term, this has to be discarded. Therefore, this must only be taken. So, if 7.5 ohm resistor were to have been connected here, the external power supplied here is same as the external power supplied here. Take another problem. A resistance of 10 ohm is connected in series with two resistances, each of 15 ohm, arranged in parallel. What resistance must be shunted across this parallel combination so that the total current taken shall be 1.5 ampere with 20 volt applied? A resistance of 10 ohm is connected in series with two resistances, each of 15 ohm in parallel. So, this is 15 ohm, this also 15 ohm in parallel. What resistance must be shunted across this parallel combination? So, in that respect, should the resistance be connected across this, or across this, or across this? as such, what resistance must be shunted. Shunted means it's as good as connecting across this parallel combination. This parallel combination means it is across this only. It is this way. What resistance must be shunted across this parallel combination so that the total current taken by will be 1.5 ampere and 20 volts is applied. Here it is almost a Ohm's law problem where V is equal to IR. Say here it has to be taken as we can see here, if I know the value of this R, these three are in parallel and that is in series with this. Since I know voltage and the current, I know equivalent resistance of this R. The resistance offered to this voltage source is known. I will call it as V equivalent. I know this, I get this R equivalent. Once this is unknown, I can get that. Therefore, R equivalent will be equal to 20 divided by 1.5 comes to 13.33 ohm. Now, what is this R equivalent? In that respect, these two are in parallel. So, this can be replaced by one resistance. What is this R equivalent? This will be 15 into 15 divided by 15 plus 15, that comes to 7.5 ohm. And in parallel with that is this R. This is 20 volts and this is 1.5 ampere. This is 5 ohm. This can be further reduced as these two are in parallel, therefore 7.5 R over 7.5 plus R, and this is 5. This will be, this is not 5, this is 10, this is 10, this will be 20 volts and this is 1.5 ampere. It can be further reduced as equal to one equivalent resistance, R equivalent, this will be equal to 10 plus 7.5 R divided by 7.5 plus R, it is this. Say I know what is R equivalent, I know expression for this R equivalent, equate those two. In that respect, 13.33 is equal to 10 plus 7.5 R divided by 7.5 plus R. On simplification, R will work out to be 6 ohm. So, that is this. Think of one more example. In the parallel arrangement of resistors shown, the current in the 8 ohm is 2.5 ampere. Find the current in other resistors, value of resistance X and the equivalent resistance. This is 4 amperes, this is 8 ohm, this is 40 ohm, this is X ohm and this is 25 ohm. In the parallel arrangement of the resistor shown, the current in the 8 ohm resistor is 2.5, this is 2.5 amperes. So, once I know this current, I know voltage across this also. It is required to find out the current in other resistors. I will call this one as a I40, this is Ix and this is a I25. In that case, the current in this will be I40 will be equal to voltage across this 40 ohm divided by 40. What is this V? V is nothing but equal to 2.5 into 8, that comes to 20 volts. Therefore, this I40 will be equal to 20 divided by 40 comes to 0.5 ampere. This is also known. the resistance is known. Therefore, I25 will be equal to, this is 20 divided by 225, that comes to 0.8 amperes. I know the current here, I know current here, I know current here, but I do not know the current here. But I know only the voltage. To find out the resistance X, I must know what is the current flowing through that. In that respect, we have this 4 ampere. This 4, at this point, it branches out to different, it divides itself to different branches. In that respect, Ix can be taken as I minus I 8 ohm minus I25 minus I40. This will be equal to 4 minus 0.5 minus 0.8 minus 2.5. So, that will be 3.8, that comes to 0.2 amperes. Therefore, X will be equal to 20 divided by 0.2, that comes to 100 ohm. That is the value. ಚಾಕ್ ಬೀಸಬೇಕು. Determine the current I1 and I2 in the partial network shown, or partial network shown. The partial network is something like this. This is 9 ampere, this is 1.2, this is 4 ampere, there is a resistance R1, this is the circuit. It is required to find out I1 and I2. If at all I want to find out I2, you can see here, this being a parallel circuit, whatever the current that is flowing here must also be flowing here. So, this is I2. To find out I1 and I2, I do not know what is value of in both of them, and at the same time I do not know what is the current at this point also. In that respect, let us start from any other point. In that respect, you will observe this is 1.29 and this is not 1.12 ampere. So, here the current will obviously be, all of them are getting added up here and it must be flowing this way. Therefore, the current flowing through this R1 is nothing but equal to 12 plus 9 plus 4, that will be 25 amperes. Though it has been mentioned as R1, it is immaterial. The current is, whatever may be the value of resistance, the current flowing in this circuit is 25 amperes. That is nothing but, this is 25 amperes. So, here it comes to, what will be the current here now? The current here is same as the current here, that will be, this is 25 plus 4, that comes to 29, minus 6, that comes to 23 amperes. So, the current here is 23 amperes. Once I know this, do I know this I2? I know this, I do not know this, I do not know this. In that respect, one of these two must be known. In that respect, we will observe here now, it is 3 ampere here. So, with that, you will observe, if I write it as say here, this current as say Z, IZ will be equal to the total current I2 into resistance of the opposite branch, that is nothing but R3 divided by the sum of the two resistances, that is nothing but this. As such, I know Iz is nothing but equal to 3 ampere. This is 3 ampere. And you will observe here now, this works out to 1.2 plus 1, that comes to 2.2 times R3. R3 get cancelled. With that, I2 will work out to be 6.6 amperes. Once I get that, I can find out the value of I1. So, the sum of those two must say here 23 minus 6.6 must give you the value of I1. So, that is how it can be done. So, that is 16.7 is the amperes. 23 minus 6.6 comes to 16.7. 23 6.3, it should have been 16.4. It has been typed as 16.7. That Consider another problem. Find the currents in all the branches of the network shown. The network is this. This is 80 amperes. This is 60 amperes. This is also 60. This is 120. This is 70. F is 30. And the resistance of all these are also given, where this is 0.02 ohm. This also 0.02 ohm, this is 0.01 ohm, 0.01 ohm, this also 0.01 ohm, and this is 0.03 ohm. Now, here when it comes to solving problem, if at all I consider the Kirchhoff's current law, I know only this current, I do not know these two currents. If I come to the Kirchhoff's voltage law, I know resistance, but I do not know what is the current in individual path. In that case, as it is, we cannot think of applying the current law or the voltage law. However, if at all I assume a current of say X here, what must be the current here? It must be 80 minus X must be flowing here. Once I assume a value of current here, so with reference to that, X can be found out also, because in a closed loop, the voltage, sum of the voltage should result into 0. Here, the current is obviously X minus 60. As X comes here, 60 goes that way, it will be this. When it comes to here, X minus 60 plus 60, it gets added up, leading to X only. When it comes to here, it will be X minus 120, and here it will be X minus 120 plus 70, that comes to X minus 50, and X minus 50 minus 30 comes to, that will be 80 minus X, it comes to it. So, with say that comes to X minus 80, it will be, in that case, this will be reverse of that. However, when you are taken this way, it can be like this also. Now, we apply Kirchhoff law in this loop. In that respect, from here to here, it is minus 0.2 X, (0.02x), then here minus, it is 0.01 X in minus 60, minus, coming to this 0.03 into X, for this minus 0.01 into X minus 120, then minus 0.01 into X minus 50. We are going against that current, therefore plus X 0.02 into 80 minus X must lead to 0. If you add up all these things, you will observe this will be 2, 3, 6, 7, 8, and this will be 2, 10. that comes to 0.1x equal to, if you add up everything, it comes to 3.9, or x will work out to 39 amperes. Once I get the value of current as 39, this is obviously now 39 ampere. The current flowing through this A to B is this 39. This is nothing but IAB. When it comes to IBC, it is x minus 39. This is 39 minus x comes to, this will be 21 minus 21, indicating the current is not flowing from B to C, but it is flowing from C to B. Therefore, you can write it as ICB is equal to 21 amperes. And here it is again 39 amperes. The current is nothing but ICD is equal to 39 amperes. Coming to this one, it is 39 minus 120 gives minus 81. The current is not flowing from D to E, but it is E to D. In that respect, you can write this one as IED as equal to 81 amperes. For this, it is this current, it is x minus 39 minus 50, that comes to 11 amperes. Minus 11 means the current is not flowing from E to F, but it is flowing from F to E. Therefore, EFE can be written as 11 amperes. And here it is 80 minus 39 comes to 41, indicating that the current is flowing from A to F only. As 41 amperes comes here, 30 amperes goes this way, and 11 ampere comes this way, indicating whatever that has been done is right. Here we will stop. We will continue with some more problems in the next class. Thank you.